Well, hello and welcome to another episode of 3D30. We're not just blowing smoke. Had a little fun with this title. 3D30 is Velo3D's LinkedIn Live and YouTube Live channel. We host this about every 2 weeks. We're trying to hold to that because of the trade show and holiday schedule. So we will try to keep up with that. But every 2 weeks, we're bringing you a new topic. So make sure you follow Velo3D on LinkedIn. We do host this channel on YouTube as well to get the latest show schedule. So for the high performance metal parts that Velo3D tends to participate in, quality is critical. We see this every day. And in fact, if you've seen some of our other shows on 3D30, you know that we've touched on this topic a lot. Laser powder bed fusion, the type of metal AM process that Velo3D uses, is a new manufacturing technology for a lot of engineers. And we realize that it's important for engineers to be familiar with the process. So today, we're going to give you a deep dive, a sneak peek, as much as 30 minutes can allow us, for never before revealed secrets of the Velo3D process, starting with the optimization of gas flow. But we're also going to go into some other topics as well. We're going to dive into multi-laser and how that creates challenges and opportunities. And we're going to look at high power laser. Lastly, if we have time, we're going to get into what is potentially the next big change for this technology that could make metal AM a major source for high volume manufacturing. So lots to cover today. Before we get started, as a reminder, this session is live and we do look forward to your questions. Love getting lots of questions or reactions. Let us know how we're doing. Give us a thumbs up. So drop a note in the comments if you have a question. We'll get to it as soon as we can. Helping me out today on this topic, we have Dr. Gregory Brown, Vice President of Technology. And we have Dr. Zach Murphree, our VP of Global Sales and Business Development. Welcome, gentlemen. How are you today?
Doing good, Mike. Thanks.
Yep, same here.
Great. Awesome. Good to see your faces. I know last week was a busy week for us. We'll get into that in a little bit. Greg, saw a recent blog on you that we posted on the Velo3D page. Learned some new things. Maybe you give folks a bit of your background.
Yeah, sure. So I'm the VP of Technology here at Velo3D. I've been with the company for a little over 5.5 years now. So relatively early on. My background is I've got a PhD in material science from UC Berkeley. Primarily was working in the semiconductor and solar field manufacturing, almost 6 years ago here at Velo. And so, a lot of the journey here has been sort of from the beginning working on the support-free technology and the ability to be able to print parts that other people can't. And then as we've evolved, that has gone into productivity improvements and next generation systems, which I think is what we're going to talk about more today.
Awesome. Thank you. Zach, you have a new title. Congratulations. Sounds like a lot of things are happening at Velo. Maybe you could give us a little bit of a background of your experience. I know you've had a lot of different jobs in that.
Yeah, a lot of different jobs, mostly at Velo. Yeah, my background is aerospace engineering. I did my PhD in hypersonics at UT Austin. Ended up getting into metal additive manufacturing after working at an oil and gas oil field service provider. Worked a little bit for one of our competitors now, that's part of GE Additive, before joining Velo, and I'll just say it, 3 weeks before Greg started. So 5.5 years ago as well. And when I joined Velo, my responsibilities were really more on the product side. So I was our director of product and was basically taking a lot of what I had learned as both a customer of metal additive and then as a salesperson for metal additive, and defining the architecture of the system, the first system that we built, the Sapphire system, along with the software that was used to run it. Transitioned a little bit more into the commercial side, and that's where I've been for the last several years here at Velo.
Nice. And in case anyone's new to Velo, could you give people a background? What does Velo do?
Yeah, absolutely. Velo is a manufacturing technology company, and we give people the ability to make complex metal parts that they otherwise couldn't make, either for technical reasons, economic reasons. Our product really is the capability to make mission critical components for any application.
And then how do we do that? What process do we use for that?
Yeah, it's an additive manufacturing process, laser powder bed fusion. So this is essentially a process where we're laying down a very thin layer of powder, 50 micron or 2/1000 of an inch thick layer of powder, and using lasers as an energy source to weld that powder to whatever's underneath it. And then layer by layer, building up a three-dimensional part.
So Greg, maybe a question for you. What are the most important aspects of getting a process like that right?
Yeah, I mean, there are a lot of considerations to be able to do this. I mean, the main thing that you're looking for when you're doing the powder bed fusion process is high density. So you want to be able to melt the powder and form, a solid metal underneath, have it attach well, have good surface finish, and also have it be completely dense all the way through, so that ultimately you can get the mechanical performance that you would expect from that particular alloy. The first starting point is having a good powder bed and making sure that's nice, uniform, and even. But a lot of where the quality issues come in from, one way or the other, come back to the optical path. We're basically using high-powered lasers that are then being redirected into the processing chamber, and those lasers are melting the powder into a liquid melt pool, and then which is then adhering to the part below it. And there's a lot of critical aspects that you need to control there. The laser power, the spot size of the laser, and then one of the big things which we're talk about today is gas flow and how to handle the welding byproducts. Because basically, as you're melting, you're bringing the powder to thousands of degrees, and you're making this liquid thing. At the same time, you also are vaporizing some aspects of the powder as well, and so you get this soot or smoke that basically is a sort of a natural byproduct of the process. And it's really critical how the system is designed in order to be able to remove those byproducts, because they have lots of impacts, and they can impact the quality of the incoming beam, which can then change your process and then cause you to start generating defects.
Okay, we had an image up earlier. Maybe you could walk us through a little bit of what we're seeing here.
Yeah, sure. So this is, this is a typical layer of a build that would be being processed on our Sapphire system. And so in the current Sapphire system, or the one that's being shown here, it's a 2 1 kilowatt laser system. And so it looks like, 2 nominally identical parts, one under each laser. And you can see, a lot of the metal's already been glazed on this particular layer. You can see that, the bright spot is basically where the laser is currently interacting with the powder and melting it and adhering it to the nearby layer. Then if you look behind it, you can see this sort of like black cloud that's coming out. And that is the soot, and which is one of the byproducts that happens when you are lasing the metal powder. And basically, if you have this black cloud, and if you don't get it out of the way fast enough, it'll interfere with the incoming optical energy, which will then, can cause issues with the beam in terms of causing the beam to be blurred out or scattering or loss of power, which then changes how much energy you're actually getting into your liquid melt pool, which will then cause your process to shift and oftentimes can cause defects. So it's really critical. That black cloud is basically one of the big things that you're trying to get out of the system with the gas flow. On top of that, what you don't actually, so you can see the black cloud, but there are a couple other things that come out of it as well. One of which that's important is just hot gas. So you're heating the part to thousands of degrees. You have very, very locally hot argon in this case. And if you've ever been on a hot road, like in the middle of the summer or something like that, and if you look down on the ground towards the asphalt, you can basically see these like shimmering lines of where you've got hot air directly above the road. That's because as you heat up gas, that changes the index of refraction, which then causes distortions basically in optical as light rays are basically passing through it. Same thing happens in the powder bed fusion system. You have a hot gas that's coming above the powder. That changes the index of refraction there. That changes how the beam is converging down to your workpiece. And if you don't effectively clear that out, you can have your beam basically change shape while you're in the middle of laser processing your part.
Okay, so we've got it sounds like the soot, or I think of it as a smoke. We've got particulates, and we've got hot gases. We kind of have the three. We called them yesterday gremlins. I kind of like that terminology. We have sort of the three gremlins. What are these gremlins doing? What impact do they have on the process?
Yeah, I mean, there are sort of large scale effects which can happen if things go really badly. Like if you generate a large amount of, you're making this liquid melt pool, that liquid melt pool also has this really hot plume of gas that's basically coming out of the top of it where the peak of the energy density is. And so out of that plume, you're getting hot argon, you're getting you're getting vaporized metal particles, which then condense into 20 nanometer spheres, which are then being ejected out. And then you also have that liquid melt pool can be sloshing around, and you can have large scale sort of like spatter particles basically detach from the melt pool and then land on your processing bed. I mean, of all of those, probably still the biggest issue is related to the hot gas and the soot as it's coming out of the melt pool and how that interacts with the beam that you're using to generate the melt pool in the first place. And like I said, the optics are basically, you've got these converging lasers, and it's coming down to a particular spot size, which is, when you're fully focused, the diffraction limited spot. But when you're doing these types of processes, oftentimes you're slightly defocusing it. If you then are passing this optical beam through soot and hot argon, you change the index of refraction, you change the optical path length, and you can cause that beam profile basically to shift as you're doing your lasing process. And this is a huge problem because at the end of the day, there's only so big of a process window you have for getting a high quality melt pool. If you have too much energy, you get one failure mode. If you have too little energy, you get another failure mode. And so what's really critical is to have consistency in that laser spot when it's working on the workpiece, because if it deviates from that, then that can cause the introduction of defects, things like lack of fusion defects or whatever that will impact the mechanical properties of the part that you're trying to make.
Interesting. So Zach, you had a role in some of the architecture choices. What are the different options? What can you do to prevent these gremlins from impacting your process?
Yeah, you'd think there are only maybe one or two real ways to do gas flow, but there are a number of different architectures that people have implemented in these types of systems. I was actually just talking to a customer today, and they described one of them as a squirrel cage, which I thought was a really interesting way to do it. But essentially, some of the machines would have gas flow that came in across the top of the machine and then did a U-turn and went out the same side that it came in. There are systems where you have essentially a jet coming from the top of the machine, impinging on the powder bed, and you have kind of a stagnation, right? So if you think about it like a hose spraying against a wall, you have the air hitting the powder bed and then spreading out in kind of a circular flow pattern. And then you have kind of a more traditional type of wind tunnel, we'll call it, approach, which is like a two-dimensional flow, where you're trying to keep essentially the velocity constant through the depth of the flow field. So that's like a rectangular wind tunnel, if you think about it like that. There are other things that people have done, such as permeable walls to kind of slowly push gas out of the process chamber. And I think this is one of the things that Greg was mentioning, that soot can actually accumulate in the process chamber. And so you also need to not only be removing the soot very close to the bed, but also not having kind of this accumulation that can cause bad effects on the mechanical properties. And there are many different pros and cons to those. I think we've chosen the more kind of standard approach that's been more straightforward to optimize, which is that kind of wind tunnel approach, which is I think the right way to go. I mean, I have an aerospace background, and when you're looking for consistent gas flow, going to a wind tunnel, a really well-controlled wind tunnel with laminarized input is what you want. Consistent gas flow at the powder bed is really kind of the name of the game for laser powder bed.
Just from a high level, if we don't have enough gas flow, we don't get rid of the particulates, the soot, and the hot gases, which was a surprise to me. I didn't think about that one. What happens if you have too much gas? Why don't you just turn it up max to 11?
I can take that one. So, I mean, like all good things in processes, there's always a process window. There's always a failure mode on the low end and on the high end. So the low end, you're exactly right in terms of not being able to get rid of the condensate and the hot gases. On the high end, you run into a different speed limit, which is that the powder bed that you're actually lasing is, in a typical case, it's like 15 to 45 micron spheres of metal powder that you're trying to melt and weld into the underlying parts. they can flow and they can move fairly easily. And so if your gas flow is too high right at the surface of that powder layer, you'll actually just blow all the powder off of the bed. And so you end up with this sort of basic speed limit where you want the gas flow to be as high as possible, but it can't be too high because you don't want to actually be eroding the powder bed. And so this puts you in this kind of window where you want it to be just high enough, but not so much. And so a lot of the tricks in order to get your gas flow right in the system have to rely on more than just pumping more and more gas into the street into the system, because there's a limit. You can only go so fast at the boundary layer, and so you need to be very judicious in exactly how you're getting the gas into the system, so that you have a high enough flow in a large enough region of the chamber itself to make sure that you're able to remove all the condensate, that you don't have any buildup, while also staying below this speed limit.
And still, I guess there's gas flow at the top of the chamber that you need as well.
Right. So I mean, they're kind of three important things to sort of consider in the process. So the first one is sort of what we already talked about. It's like the locally generated soot and hot gases that you're making right where the laser is. You need to get that out of the way as fast as you can. The second issue is that, especially when you're in a system with multiple lasers, the byproducts that are basically being removed, you want to make sure that they go immediately out of the process chamber, and that they don't recirculate anywhere, because if they recirculate, they can basically hang out on the upper regions of the chamber, and they can interact with not just the laser beam that generated in the first place, but interact with all the laser beams that are being used in the system at that moment. And so you got to get the condensate away locally and then away globally as well. And then the last aspect is there are a couple really critical windows or optical pathways within the system that need to be kept completely clean the whole time. And so the biggest one there is the process chamber, where you're doing all of your dirty work, is separated from your optics box, which is where the laser light is ultimately coming from. And that interface between the two, that window, is super critical to keep clean, because if you end up with any metal condensate that ends up on that particular window, what will happen is it'll start to absorb some of the incoming laser light that's trying to pass through it. Once, that causes two problems. One is you get a loss of power, but the bigger problem is actually that condensate will then absorb the laser power. It'll start to heat up. It'll heat the window up. The index of refraction of that optical media of the window changes as a function of temperature. And so what effectively it can become an additional focusing element, which causes your beam to basically start to converge faster than you were planning on. And ultimately what that causes is unstable spot size. And so it's super critical to have good flow sort of in that region to avoid any of the condensate getting to those optical windows as much as possible. And so to do that, you have sort of your main flow that's removing the gas, right near the bed. But then we also have, a number of other gas flows up closer towards those optical windows, which are helping to basically keep them clean and also prevent recirculation of the soot within the system.
There's a lot going on. You did say something that kind of made me wonder. You said for multi-laser systems, this is harder. And I know we have the XC coming with 8 lasers. What are the complications that come in with a multi-laser system?
Yeah, I can take that one. I think with the 2-laser system, you definitely have complications around like laser alignment that we've done a really good job of addressing. The nice thing about a 2-laser system, though, is that you can essentially keep the lasers out of each other's way very effectively. When you start to take a 600 millimeter build plate like the XC and put 8 lasers on it, then it becomes much more difficult to have the lasers working in an area that doesn't affect whatever's going on downstream of them, right? So you don't want to have a laser producing soot where that soot is then going into a region of the build plate where another laser wants to be working. This is the don't shoot the smoke rule. And really, I think what that comes down to is system design and a lot of times efficient scheduling. So making sure that your lasers are operating either close enough to each other that they're not going to impact each other's process from the soot that's being generated, or sequence where they're essentially never downstream, never in this cone of influence of this soot generation from the upstream laser.
And I mean, what about heat with 8 lasers? That's got to generate a lot more of the hot gases that we were talking about before.
Yeah, I mean, 8 kilowatts of energy input is significant. I think there's also a lot of thermal considerations that we've made in this system, which remove some of that the thermal energy. But again, you do need to be very careful about the hot gases generated locally and their effects on any of the downstream energy being delivered to the bed.
Yeah, interesting. And as a reminder for our audience today, live session, so please feel free to bring in your questions. We've got Zach and Greg here, great resources for you. If you want to know anything about our process, I mean, these guys are telling me stuff I've never heard before. So this is a great session to get your questions answered. So let me kind of jump forward a little bit here. I think you sort of gave us a hint on which one we chose. I just wanted to kind of back up and make sure we had the U-turn model, we had the top down, and then we had the wind tunnel. And in which direction did Bella go, and why?
Yeah, wind tunnel. I'm not going to say it's my fault being an aerospace engineer, but I just think it's a much more efficient way. I think if you look at things like the top down, like the jet with the stagnation, there are some interesting reasons that you might take that as a solution, right? If you think about what's happening, you have a jet that's hitting the build plate and then spreading out in all directions. And so if you had a number of lasers arrayed in kind of a circular fashion, all of their soot would be going towards the edge of the build plate, which means that from a scheduling perspective, you can eliminate some of those complications and difficulties. The problem is that then your gas speed is kind of a function of where you are on the build plate, right? And immediately under that stagnation point, you have essentially no gas flow, and then very high velocities that fall off pretty rapidly as you approach the edge of the build plate. So when you're looking for a consistent gas flow, a consistent speed, it's not, I think, the best approach. And then the U-turn model was not great because essentially what you end up with is a standing vortex in the middle of the build chamber, right where your lasers are trying to shoot through. And that can gather up soot and lead to serious issues, especially when you're melting a lot of material per layer.
Nice. So, Greg, did he choose a good one for you, for your team?
Yeah, no, I think so. And I think, I mean, one of the challenges too that we found when we were developing the system is, from a productivity perspective, you want more lasers and you want more power because you basically want to be able to melt more cc's of material, on any given second. And that helps you, increase the productivity of the system, spread the cost of the system over, over a larger number of parts, and ultimately drive the cost of the parts down. The real challenge, once you start getting to high power and multiple lasers, is just the quantity of certain and lasing byproducts that you're making within the chamber. And so, especially what we found, if you're running a lower power process, say like a 200 watt or even a 400 watt, core type of process, you're generating, soot at a certain rate. You can sort of get away with not having that high of gas flow or relatively inefficient gas flow, because ultimately you're not making that much pollution that you have to get out of the way. But once you start getting to a kilowatt, the amount of soot that you're making per second increases proportionally to that. And so you just need a lot of gas flow to actually get all of that soot out of there. And the more lasers you have, obviously the more that you need. And so I think the wind tunnel approach, allows us to get to the overall volumes of gas that we need to be able to push out of the chamber per second. That's really necessary to run, very high power with all the lasers on all the time without having them basically, smoke themselves out.
So we do have a couple of questions from our audience here. Sean is asking, how is gas flow monitored at the surface?
So the gas, so there are a bunch of different ways that we can do it. So generally in the system, the gas flow is controlled by pump, and there's a mass flow sensor in one of the inlet tubes, basically leading into the system, that is measuring what the actual flow rate is, and then that is then controlled by the software to keep that constant over time. Because we haven't talked about it yet, but downstream of all this, you've got this filter that's basically removing the soot byproducts out of the gas. And so as you get a delta pressure across that, you need to compensate your pump speed to basically keep the same amount of flow going into the system at all times, so that your process stays nice and consistent. There are sort of offline ways to measure with like an anemometer to actually measure what is the local velocity of the gas, and so that's definitely something that we've done a lot of when we were designing the gas flow originally. But one of the things that we've also moved a lot to is that we utilize some of the unique sensors that are on the Sapphire system to come up with other methods or metrologies that allow us to effectively determine what is the local gas flow by looking at breakdowns in processes. So we can basically, if we have a process, we know exactly how it breaks. We can use that and use test patterns to basically map out on the build plate exactly where the breakdown is happening. And so from that, we can then infer what is the localized gas flow rate. So that's something that we've sort of developed as a much sort of faster way and more quantitative way to make sure that the gas flow is good on every system before it goes out the door.
Nice. And this one maybe is, Zach, going back to your original choice of the mainframe, vacuum chambers. Have we looked at a vacuum chamber? Do we think about it? And what would be the pros and cons of using vacuum?
Yeah, so we didn't seriously consider, I don't think, operating in a vacuum atmosphere. We operate in an extremely low oxygen content argon atmosphere. Vacuum chambers are, I think, per the comment, they can be difficult to maintain, although we've managed to build a system where we can maintain sub 10 ppm oxygen in the chamber. I think one of the other things that we really wanted to make sure we were doing was designing a system where if anything were to fail, it doesn't leak oxygen into the machine. Because especially when you're processing reactive materials like aluminum and titanium, you don't want to have an oxygen leak into the machine, right? So if you're in a vacuum system and you have a leak, it's going to pull ambient air into the machine, which could cause a real safety issue more than anything else. So that was one of the main considerations for how we built the system.
And maybe, Greg, this is a good one for you. Are there aspects of the powder that can reduce the occurrence of soot in the first place?
Yeah, that's a really interesting question. There's kind of like the simple answer and then the more complicated. So in the simple case, we definitely have seen cases of powders where it's not necessarily that you get a change in soot, but that spatter mechanism that I mentioned before, where you basically can have the melt pool break off while it's still liquid, you can have a piece of liquid basically break off and generate spatter, solidified large particles on the bed. We definitely have seen issues with powder in terms of that, especially if you have some level of contamination in the powder, something like that, high water, something of that sort, where you can sort of get an excess of spatter from different powder characteristics. And I know that there is some sort of, there is a fair, the actual interaction of the laser beam with the powder is quite complicated in terms of ultimately, what does your temperature distribution look like in your liquid melt pool? And so I have seen, that there are some studies, indicating that, one powder versus another, that you can actually physically change the amount of vapor or soot that you're basically generating per, cc that you're lasing. So there are some interesting directions in that. It does seem to be, it's kind of on the margins. It seems like there's kind of like for a given material and a given type of powder, you generally seem to make about the same amount of soot per cubic centimeter that you're lasing. But I know that there, since, it's a major, impact in terms of system cost and productivity in terms of trying to reduce the amount of soot that you're making. I know people are going in all sorts of different directions, including looking at tailoring the powder in order to try to reduce the generation rate to begin with.
And you mentioned materials. So are there differences between different materials, like aluminum and titanium would be different?
Yeah, for sure. We've seen that. So, I mean, there are a couple different aspects. One, like I mentioned before, in terms of that gas flow process window, there is a challenge with the powder erosion, or basically the upper speed limit of how high you can turn up the gas. Is a strong function of the material density, because basically the lighter particles or the lighter materials like aluminum are just much easier to blow away. And so that changes your window in terms of how high you can go on the different materials. And also the amount of vapor or condensate that you sort of make per cc of lased material also does seem to be material dependent, where some materials are inherently sort of sooty and more spattery than other ones. And which kind of ties back to that last question. That's why there's a lot of active research right now trying to figure out exactly what are the knobs that you have to minimize that, and how do you drive it down further so you can make the gas flow situation easier and ultimately go to a higher productivity system.
So we have another question here from Dustin. Do you believe that as-built surface finish is primarily driving laser parameters powder deposition, or the efficiency of quickly removing soot from the build area?
As-built surface finish driving, not so much. So I mean, I guess it depends on what you're asking there. So I mean, generally in all these laser powder bed fusion processes, you have some sort of bulk infill strategy where you're making the bulk of your material, and then you have some sort of skin where you're doing a secondary pass to try to reduce the surface finish. In terms of what matters from the soot perspective, most of it is coming from that bulk infill, because it's sort of it's sort of directly proportional to the number of cc's that you're lasing, and the bulk of the material is generally higher than the surface of the material. So a lot of the parameters and gas flow considerations and stuff like that are all driven around minimizing the influence of the soot when you're doing the bulk fill. But it does matter in terms of, but it does ultimately tie back to surface finish, because what we have seen is that if you don't have good gas flow in the system, if you do have recirculation of soot and condensate, basically after you do all the infill, if that stuff is still hanging around inside of the chamber, that'll influence the optical beam when you're doing these skin passes, which oftentimes are a lot more sensitive and have a much smaller process window that you can actually work on. So that's where it becomes really critical, where if you want to have a good surface finish, it sort of forces you to either have really good gas flow to remove all the condensate, or in some cases, for systems that aren't designed that way, oftentimes you have to have like delays or things like that, where you basically are just waiting for the soot to get out of the system before you then go back and you do your skin passes, which obviously hurts, productivity, throughput, and ultimately drives the cost of the parts up.
Okay, I'm going to ask one more audience question, and then we'll do our finishing comments here. I notice we are over our 30 minutes, our branded 3D30 minutes. Does optimizing the gas flow lead to less in-process powder contamination in your experience?
I'll leave that one to Greg for sure.
That's an interesting one. So, I mean, definitely in the sense, if you have very poor gas flow, with respect to spatter, especially, if you have very poor gas flow and you get to the point where you have, large amounts of material coming off of the liquid droplets and condensing and landing on the surface, that effectively makes oversized particles. And so that when you're then going to recycle your powder, usually you put it through a sieve. So like on our system, there's an onboard sieve that's constantly, cleaning the powder out. If you have very poor gas flow, yes, you can have a lot of spatter, which then leads to that material will then get sieved out, which, again, increases the amount of material you have to load into the system to get a certain amount of cc's out. So it definitely matters from that perspective in terms of reducing the amount of contamination.
Okay. So that is all the time we got. I'm going to do some two finishing questions here, and Zach, I'll let you go first because Greg just finished up. What do you see maybe in the near term, let's say next year or two, that can revolutionize this technology and push it forward?
I think the main things that we're seeing are kind of drives towards new applications, and that's being enabled in large part by essentially some of the newer systems, right? Some of the higher productivity, larger part types of systems. So as an example, we have the Sapphire XC system being delivered in 2 months to the first customer, which is the 8 kilowatt, 600 millimeter diameter machine with a 550 millimeter Z height. But towards the end of next year, we'll also have that machine in a full 1 meter Z height. So you definitely are seeing an expansion of build volumes to accommodate larger parts and different applications. But also a dramatic increase in throughput. And the throughput increase is really critical because it drives the part cost down by a pretty significant amount. And that starts to pull in these new applications that on some of the current systems may not make good sense economically. And so, I'm pretty excited about some of the new applications that we're running across that may not have made a lot of sense 2 years ago, that all of a sudden are really kind of almost no-brainers for metal additive manufacturing coming into these new high extra capacity types of systems.
Cool. And Greg, what's your view? Maybe longer term, where do you see this going?
Yeah, I mean, kind of piggybacking on what Zach said, like right now, more lasers, more power seems to be the direction to go in order to drive down the cost per part. And with that comes stricter requirements on gas flow, needing to have really, really high gas flows and very good control of it within the chamber to make sure that you're able to get rid of all those byproducts. I know that there's at some point, it's kind of like the simple way to solve the problem. I know that there's I'm interested to see, there's a lot of research going on, externally and then also sort of internally within the company about, can you change any of the fundamental, parameters which can change that equation at all? And one of them is, what is the actual soot generation rate that you're doing when you're lasing a certain amount of cc's? And same thing with how much energy are you actually putting into the part versus how much are you then using on wasteful byproducts like hot argon and soot and things like that. And so I think there's a lot of room there to change how much soot is generated per cc, which can then lighten the load on the gas flow requirements. And so one of the things that I've seen that's interesting is tailoring the laser beam profile. Right now the conventional way to do it is Gaussian profiles, and when you're doing these bulk strategies, oftentimes it's just a defocus Gaussian. But there are other, there's a very wide variety of laser profiles that one can do, and potentially manipulating those in a way that allows you to melt the same amount of material, but having a lower overall peak temperature, which would reduce the amount of vaporization of metal that you get. That could be a really interesting way to reduce the amount of, soot per cc's, which then will allow us to then, put more power, more lasers with the same amount of gas flow, which I think would be very valuable sort of longer term.
Wow. I always learn something when I talk to, if I can get Greg and Zach to sit down for 30 minutes, I'm definitely going to learn something. And so I want to thank you for your time today. I picked up a ton. I'm sure our audience did as well. Audience, thank you for joining us. I know we ran a little bit over, but we wanted to get to your questions, and that's always a focus for us on these sessions. It's live, it's interactive. We want to keep it that way. So remember to follow Velo3D. Keep up to date. We are going to have one in 2 weeks on the 28th of October. I've already had my first call on that. That is going to be pretty awesome. I'm looking forward to that one. I'm not going to tell you what it is. Follow Velo3D to find out. And again, thank you to our panelists, Greg and Zach.
Thanks, Mike.
Thanks, Mike.